Aduh. Aduh. Okay, Assalamualaikum and good morning. Is everybody here? Okay. So we cannot go to the lab tomorrow. Right. Okay, while waiting for your friends. Okay, we have here 26. 4 is missing. Okay, 4 students are missing. Who is missing? One ada. Is one here? I know we have 2 ones here. One ada. You is. Are you here? Ada. Haziq. Hafiz.
Ada doktor?
Anas. Ada ke? Anas ada.
Ada doktor.
Apa yang tak ada ni? Seri ada Seri.
Ada.
Ada. Okay. Okay, let us start. Before that, I want to share video. I'm not sure whether I have shown to you this video. Have you seen this multiplexer and the multiplexer? Have you seen this video before?
This I, Professor Ritesh Dolakia, is going to explain
No?
you
Okay,
designing of 4x1 multiplexer using 2x1
let
multiplexer.
us see this one.
So in my previous video of month,
Okay,
welcome to
I start
Digital
again.
Electronics Lecture
Okay.
Series. I, Professor Ritesh Dolakia, is going to explain you designing of 4x1 multiplexer using 2x1 multiplexer. So in my previous video of month 3, I have explained how we can identify requirement of total lower order multiplexer to get higher order multiplexer, right? So first, here we are dealing to identify how many 2x1 multiplexer is required to get 4x1 multiplexer. And see, to have this answer, all we need to do is we need to divide higher order by lower order. So here 4 by 2, higher order divided by lower order, 4 by 2. And again we need to do same thing, 2 by 2. So this is 1. And as if this division is resulting into 1 or less than 1, we need to stop that division, right? So total requirement is 2 plus 1, means total we need to have 3 multiplexer of 2x1 to get 4x1 multiplexer. Now let me explain you the basic truth table which is there with 4x1 multiplexer. So if you see 4x1 multiplexer, then there are two selection lines, S0, S1, and we have Y. And in that, see if S0 S1 that is 0 0, in that case let us say first input that will get selected, which is I0. If S1 S0, if it is 0 1, in that case I1 will get selected at output side. If it is 1 0, then we will be having I2 selection. If it is 1 1, in that case we'll be having I3 input selection at output side. Right. Now here this is what we are doing to make it by having 2 cross 1 multiplexer. So see here 2 1, that is how connection is there. So first I'll have to place 2 cross 1 multiplexer like this. And here we have 1, so I need to place 1 multiplexer of 2 cross 1 multiplexer, right? Now as all these are 2 cross 1 multiplexer, see we have 2 inputs and we have 1 output, and this output that we are going to connect over here, right? So now we can say, see these are I0, I1, I2, I3, and this is my output Y. But the major question which is there with this interfacing is, what will the selection line? So first thing that you need to understand, see selection line for this two will be same, and other selection line that will be there with this multiplexer, right? Now how to identify S1 is over here and S0 over here, or S0 over here and S1 over here? So for that, let me give you some cases. So as if I consider this is 0 and this is 0, then what will happen? From this multiplexer, I0 will get selected. From this multiplexer, I2 will get selected, and this will be now input to this multiplexer, and as this is 0, I0 will get selected, right? Now let us consider second case. So in second case, let us place 1 over here and 0 over here, right? So you see, as this is 1, here I1 will get selected, and as this is 1, here I3 will get selected, and as this is 0 over here, here output will be I1, right? So what is my output? I0, I1 for 0 0 over here. So here we have 0 0, means S1 is 0 0, right? Here I0, I1 output is there with 0 0 input of selection. So that is what the case which is there with S1. So we can say here we have S1 terminal, right? And here obviously 0 1, that is what the data. So we can say here we have S0 terminal, selection line is there, right? So see, this is how this mux tree that we can have it to have 4 cross 1 multiplexer by using 2 cross 1 multiplexer, right? Now in next video I'll explain you how we can design 8 cross 1 multiplexer by using 2 cross 1 multiplexer. So that will resolve your doubts further. I hope that you have understood this video. Thank you so much for watching this video. Please do give your valuable suggestions. The reason is based on your suggestions in future, I'll make videos which will resolve your query.
You always hear people say, this year, I want to make.
Okay, so you understand how to design using multiplexer? Okay, I think the professor has clearly explained how to design it. Okay?
Doktor,
Ya,
ada orang nak join.
ada orang nak join. Siapa yang lambat tu? Siapa dia? Akasha. Dah masuk belum? 29 sekarang ni. So 29 saya punya divide 2 masuk sini. So 27. Ada 3 orang lagi. Siapa lagi belum masuk? Cuba cek nama-nama dia. Aiman dah ada, Akasha, Aminah, Amirun, Farah, Hasif, Edina, Izzat, Muhammad Anas, Muhammad Fadhi, Muhammad Hafiz, Muhammad Haziq, Muhammad Imran, Muhammad Najib, Ni Akif, Nur Khairina, Nur Syamimi, Nurin, Nurul Adlina, Pradip, Safwat, Seri, Shishilia, siapa baru masuk ni? Tan, you baru masuk. Who else? Amirul ada, Muhammad Amirul Hazmi. Nurin, Tan, Farah ada, Farah Hanani. Farah Hanani ada.
Ada doktor.
Wan Nur Adlin, you, Muhammad Akasha, Muhammad Hafiz, Pradip, Muhammad Izzat. Ada? Muhammad Aziz Azidin, Izzuddin ada?
Ya saya Doktor.
Okey, Syamimi, Muhammad Najib. Amir Sufi ada?
Ada Doktor, ada.
Amir Sufi ada. Okey, Nurul Adlina. Nurul Adlina ada?
Ada.
Ni Akil, Aiman Iqbal?
Ada Doktor.
Ada. Wan Adana, Muhammad Haziq, Muhammad Imran, Amirun Fahim. Ada?
Ada Doktor.
Amirun Fahim. Ada ke? Ada 2 orang lagi tak ada. Seorang lagi tak ada. Okay. So tak apa. Okay. Have you seen this video?
Hey everyone, so this video is going to be about
This one a good one
decoders.
also.
Make it as quick as possible because it takes of
This is about encoder and decoder
10 minutes long and stuff when it really doesn't need to be. So let's get started here. An encoder, the basic idea behind an encoder is that it will take multiple inputs, as seen here, and will turn it into only a few outputs, as seen here. Decoder is the same thing except that it does the opposite. So it will take very few inputs and will turn it into multiple outputs. So the way that we find out how many I variables or j variables there are with the number of x, y, z variable type things that we have. So if we have x, y, and z, that means that we have 3 variables coming out of here. What's 2 to the power of 3? That's 8. So in terms of an encoder, if we have 3 outputs here, then we're going to have 8 inputs. And for the decoder, if we have 3 inputs, then we'll have 8 outputs. So I'm going to cut out for a second while I put up some truth tables, and we'll fill them in together. Okay, so this is the truth table for an encoder. So it's kind of similar to a multiplexer in that we're still kind of dealing with cases or conditions. So when x, y, and z, oh crap, I'm still getting used to OneNote. I have no idea what's happening half the time. When x, y, and z are all 0, that means that our input will be our very first input, just because this is the first kind of condition of x, y, and z. So that will be 1. And we're just going to iterate all the way down. It's going to kind of form like a bit of a diagonal type thing. So I'm going to fill in some zeros. So we'll use green for that. 0, 0, 0, 0, 0, 0, 0. So you're only going to have one value on each row of inputs from the encoder. Alright, so now we're on our second condition. So another way of saying it is that if the input is I1, so if you have I1 is equal to 1, then x, y, and z will be 0, 0, 1. So we'll do our zeros now. So remember, we only have one value per row of inputs. And we're just iterating down. We're just going down the list. So now I1 is 0 because we're on the third row now. Okay, so I think you guys get the idea. So I'm going to cut out and fill out the rest of the table. Okay, so this is our completed truth table for an encoder. And as you can see, we have kind of this diagonal thing here. I'll just retrace the one so we can see it better. So again, we're just kind of going down the list here. So we have input 0 here, which is our very first input at the top, right here. And when that is 1, then we'll have 0, 0, 0 for x, y, z, and then we just kind of go down the truth table. So now we're going to look at decoders. Okay, so decoders are really just the opposite of encoders. So I took the truth table from the encoder that we just did, and I just reversed it. And it's honestly, it's the same concept. So I'm just trying to change the cursor so I can follow it a little better. So when we have x is 0, y is 0, z is 0, which is this condition here, first condition, then I0 will be 1. And again, we can only have one value per row of outputs here instead of inputs. So it's the same thing, except that we're just really looking at the x, y, z. So when x, y, and z are all 0, our first output will come out. I actually forgot to label this as being j. So these are all j values. And it doesn't really matter what you call these. But just for clarity, I want to differ. I hate that. I wanted to differ the encoder input from the decoder output. So those are all j values. So x, y, and z, when x, y, and z are all zeros, then our first output will go out. When x, y, and z are 0, 0, 1, our second output will go out. It's just based on conditions. So again, we're just iterating down the list here. So we go from, where's my cursor? There it is. So we go 1, our first condition, to our second, to our third, to our fourth, to our fifth, to our sixth, to our seventh, to our eighth. And we're just following the diagonal once again. So I hope that was helpful. That's pretty much it for encoders and decoders. Feel free to suggest ideas for other videos in the comment section or to ask questions in the comment section. So thanks for watching. And
For just $67.
Okay. For encoder and decoder just now, if you look at how to go back? Macam nak patah balik? Aduh. Okay. If you look at this encoder and decoder,
so
this
video
is
about
for look at for decoder. This is for active high output. Remember in your notes, the example are based on the active low output. Remember when you have all 0, for example, if you have input for x, y, z is 0, 0, 0, so your j naught will be what? Will be low and the rest will be high. Okay, but here in the example here, this is active high output. Okay, if you still remember. So, are you guys still with me here? Okay, so now I will like to continue with counters, ya.
Doktor, ada
Ya.
orang lagi nak masuk.
Ada lagi orang nak masuk?
Ada.
Kejap Siapa dia? Siapa yang baru masuk?
Azmi.
Ad-
Amirul Azmi.
Haziq dah left pula.
Ada. Saya
Okey, dah cukup dah 30 orang. Ada yang masuk 2 orang ke? Satu nama, 2 device. Okay, so now I would like to continue with counters, ya. Mana dia? Sekejap. Kenapa boleh jadi PDF? Kejap Sekejap. Salah ambil dokumen. Okay, can you see the slide? Okay, this is counters, ya. Okay, counting in binary. Okay, this is very basic. We have gone through this. As you know, the binary count sequence follows a familiar pattern of 0 and 1s as described in this section 2.2. Okay, you know how to tabulate this. Okay, even though this is very easy, some of you did not do it properly in your test. Okay, so remember this, the column on your right here is the least significant bit. Column on the left column here is the most significant bit. So here is 2 power of 0, 2 power of 1, 2 power of 3. So 2 power of 3 you have 8 bits, ya. Because 2 power of 3, 2 times 2 is 4, 4 times 2 is 8. So that's why you have 8 bit here. Okay, 8 possibility here. Okay, so here 2 power of 0. So 2 power of 0 is equal to 1. So you have 1 0 1 1 1 0 1 1. 2 power of 1 here, so you have 2 power of 1 is equal to 2. So you have 2 zeros, 2 1, 2 zeros and 2 1. Here 2 power of 2. 2 power of 2 is equal to 4. Okay, so 4 zeros and 4 ones. Okay, least significant bit changes on every number. Okay, as highlighted there. And the next bit changes on every other number. Okay, so this is highlight in blue there. And then the next bit changes on every 4th number. Okay, so now this is a counter can form the same pattern of zeros and ones with logic levels. So the first stage in the counter represents the least significant bit. So this is the first stage here on top here. Notice that these waveforms follow the same pattern as counting in binary. So if you look at here, this is the first stage, you have 0 1 0 1. Okay, and then you have second stage here 0 0 1 1 and so on. And the third stage here you have 0 0 0 0 and then 1 1 1 1. Okay, similar like what have tabulate just now. Apa sebenarnya cursor ni? Okay. Okay, so now you can see this pattern here, or we call this the timing diagram here. Now the top here is the least significant bit and the bottom one is the most significant bit. So if you look at the counter here, the most significant bit here, so 0 0 0, here is 0 0 1, 0 1 0, 0 1 1. This is equivalent to what? 0 1 2 3 4. 5. 1 0 1 is 5. 110 is 6, 111 is 7. Okay, now we look at 3-bit asynchronous counter. Okay, so pay attention here, you have asynchronous here. So in an asynchronous counter, the clock is applied only to the first stage. So at the first stage, you see here, this is called the first stage, second stage, and this is the third stage. So the clock is only applied to the first stage. Okay. And then subsequent stages derive the clock from the previous stage. Okay, so now stage 2, the clock comes from stage 1 Q bar. Okay. Stage 3 here, the clock comes from Q bar of the previous stage. Okay. So the 3-bit asynchronous counter shown is typical. It uses JK flip-flop in the toggle mode. How do you know this is in the toggle mode? You look at the J and K here. J and K is connected to one point that is too high. Remember, when J and K both are high, they are in toggle condition, or toggle mode. So this is asynchronous. One clock only applied to the first stage. The following stages, stage 2 and so on, the clock comes from the previous stage. Okay, for example here, second stage, the clock comes from first stage. Third stage, the clock comes from the second stage of Q bar. You can design, sometimes some of the design from Q bar, some of the clock comes from Q naught only. Okay, not Q bar. It's up to you. You design it. Okay. So waveform are on the following slide. Okay, you can see here. Okay, this is a 3-bit. When you have a 3-bit counter, meaning you have 3 flip-flop. Okay, for example here, 3-bit asynchronous counter here, then you have 3 flip-flop. 1 here, 2 and 3. Okay, notice that the Q naught output is triggered on the leading edge of the clock signal. Okay, the following stage is triggered from here, Q naught bar. The leading edge of Q naught bar is equivalent to the trailing edge of Q naught. It's just opposite, So the resulting sequence is that of a 3-bit binary up counter. Okay, so this is a 3-bit up counter. How do you know this is a 3-bit up counter? You look at the sequence here. Here is 0, 0, 0, and then going up to 0, 0, 1, 0, 1, 0, 0, 1, 1. It's going up. 0, 1, 2, 3, 4, 5, 6, 7, and so on. So this is what? Binary up counter. Okay, and the clock for the second stage here refer to the Q naught bar of the first stage. Q naught bar stage is just opposite of Q naught here. So instead of Q naught bar, okay, so you can also look at Q naught. Faham? Okay?
Doctor, if we connect Q naught to the second counter C, then is it means that Q1 will be comes 1 when it is on?
Q1, you mean this part here is connect to here? You mean Q not here?
Connect to the C.
Connect to?
The C.
See, you can connect this to here, but you look at the edge here differently.
It will become the leading edge of Q naught, is it?
It will become what?
It will become, the Q1 will depends on the leading edge of Q naught. Here is the, no, here is the, here,
read here. The leading edge of Q naught bar is equivalent to the trailing edge of the Q naught. See? So instead of you look at here is the trailing, you now because you don't have Q naught bar here. For example here, there is no Q naught bar, right? Okay. So you only have here Q naught because you refer to this JK flip-flop. Okay, so this is the point here because this is positive, so it's positive here. Okay, so for Q naught here, see the Q naught here, you change every, I say positive lah, senang. Instead of leading, trailing, okay. It's a positive edge. So this is a positive edge here, so it change at every positive edge here. Okay, but now this Q1, okay, Q1 the clock is connected to Q naught bar. Okay, Q naught bar here. Okay, you don't have Q naught bar here. Okay, how do you draw the Q naught bar? It's just opposite of this Q naught. So when this is low, it's going to be high, low, and so on. Okay, now you only look at Q naught. It's much easier. But now the edge that we are looking at is at this negative edge. Okay, it changed at the negative edge, no longer at positive edge. Okay, if you don't understand, you can try. Okay, go back. You're already at home. You draw this again, Q naught, and then you have another one here at below Q naught. You draw Q naught bar. Okay, and then you draw Q1, and then you draw Q1 bar below Q1 here, and then you draw Q2, and then you draw Q2 bar, and see whether you get the same. I'm sure you will get the same timing diagram. So it will give you more understanding. Okay, when you draw it. Okay, Tan?
Okay.
Can you do that, Tan?
Yes, doctor.
You do that. So you can see it and you won't get confused. Because it just Q naught bar and Q naught is just inverse. Okay, instead of positive edge, it becomes negative edge. Okay, something like that. Okay.
Okay, thank you, doctor.
Okay, now look at propagation delay. Asynchronous counters are sometimes called ripple counters because the stages do not all change together. Okay, why? Because remember, the clock is only at the first stage. So for certain applications requiring high clock rates, and this is a major disadvantage. Okay, notice how delays are cumulative as each stage is in a counter is clocked later than the previous stage. Okay, now you look at the delay here. You can see here. Okay, for example, the first stage, the delay, you can see Q naught here. There is a small time here. So Q naught is delayed by one propagation delay. It's called one propagation delay here. Okay, so when the first bit already delay, of course the second one, the second clock, you have already delay and so on. Okay, this much delay. And then look at the second stage. Because the second stage, the clock comes from Q naught here, right? Or Q naught bar. So you have a delay here. You see here, this is Q naught, and then Q1 is here. So you have a delay here. Okay, and then for the third stage, and then the third stage, the clock refer to Q1. So this is the Q1 just now, already delay. Now you have some more delay. Okay. So this here you already have one delay here. See the first stage here, one clock here, one delay, and then you have two delays, and then here you have three delays already. Okay, it's cumulate. So by the time you reach the third stage, you have three delays. If you have more, then you have more delays, right? Okay, that is the disadvantage. Because the clock you have there is only at the first stage, and the second stage refer to first stage, and the clock for the third stage refer to the second stage. Okay. So now look at this 4-bit asynchronous binary counter. So when you design 4-bit asynchronous counter, you have 4 flip-flops. So you have 1 here, 2, 3, 4. 4 flip-flops. Okay, this is labeled as FF0, FF1, FF2, and FF3. Okay, so here is the least significant bit, and here is the most significant bit. Yeah. Okay, and then you look at here, the J and K here all connect to one point that is to high condition here. So meaning J and K both are high. Both are high, they are in the toggle mode. And then you look at the clock there. The clock is
Negative.
Yes, at the negative age. Because you have this bubble. So the clock is only applied to the first stage. The second stage here comes from Q0 here. Okay, Q0. The 1, 2, 3. Okay, third stage, clock come from Q1. The fourth stage come from Q2. That is on the negative age. So this already drawn for you, the negative age. Okay, so now look at the waveform or the timing diagram for Q0, Q1, Q2, and Q3. You see you have here, at this negative age, it change clock because, change state because this is always toggle, right? So start from low and it becomes high, low, high, and so on. And then Q1 is here, the clock refer to Q0. Q0 is here, is negative age here, so low, start with low and then become high, and then low, high, and so on. And then you look at Q2. Q2 here is referred to the clock of Q1. So this is the Q1. Q1 becomes clock to Q2. So this is the negative age, and so on. So start from low and then goes high, and then goes low and high, and so on. And then finally the last stage here, Q3. The clock refer to Q2. This is Q2, negative age is here. So it start with low and then it's going high, low, and so on. So this is the counter where you take the reading here. So you have here low, that is 0. Low, high, 1. Low, high, low, 2. Low, high, 3. Low, high, low, 4. Low, high, 5. Low, high, low, 6. Low, high. This is 7, and so on. Do you have any question? You don't have any question? Wait, I want to have your name here. Nanti senang saya nak panggil. Okay. Okay, so asynchronous decade counter. Okay, decade counter. What is decade counter? What is decade counter? you have 10 bits. It's only count until 9, right? 0 until 9 you have 10. Decade. One decade how many number for one decade?
4 digit. 10 number.
10, right? Okay. So this counter uses partial decoding to recycle the count sequence to 0 after the 1001 state. So the flip-flops are trailing edge triggered. Okay, trailing edge triggered, see, because the clock you have bubble there. So clocks are derived from the Q outputs. Okay, other truncated sequences can be obtained using a similar technique. Okay, so if you look at the this counter here, the J, K all connected to high. So it is always toggle. Okay, and then the clock connected to Q. You have bubble here. So you look at the trailing edge or the negative edge. Okay, and then you have what gate is this?
And gate.
Okay, you have NAND gate. So NAND gate here, it's real clear. When it reach 1001, it will stop and then it start to clear the next stage here. Okay, so if you look at here, Q1 is connected to NAND gate. Okay, and then Q3 connected to Braille NAND gate. Do you have any problem? Do you have any question? One entry. Tak, no. Okay, I want you to go back and draw the timing diagram for Q0 there, Q1, Q2, Q3, and see how the timing diagram looks like. Because now you have here the NAND gate. Okay, can you do that?
Yes, sir. But doctor, why only Q1 and Q3?
Why? That's why I asked you to go to draw the timing diagram and see what happened. Okay?
Okay.
Okay. See, it's already drawn for you. Okay, when Q1 and Q3 are high together, the counter is cleared by a glitch on the clear line. Okay, so see why this happening? Okay, now look at here. This is the clock. And this is bubble. So you look at the negative edge. Okay, now look at the Q0 first. So you draw the timing diagram for Q0. Q0, there is no problem. You just draw, change at the negative edge. Okay, so you have low there, high, low, high, low, high, and so on. Okay, until 10 here. Okay, because you have up to 10 here, because decade. And then you draw Q1. Q1 here is the output refer to J1K1, which is always toggle, and then the clock here refer to Q0. And look at this at negative edge. So Q0 and negative edge is here, 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 here. So you have low, high, low, high, low, and so on. And then you look at Q2. Q2 is connected, Q2 is referred to J2 and K2, also always toggle. And then the clock look at Q1. So this is the Q1, negative H is here. So you have low and then high, okay, and low. And then Q3. Q3 refer to J3 and K3, always toggle, and the clock refer to Q2. So Q2 is here, okay, and you have bubble, so the negative H is here. It's only change state here. So you have low and then you have high. Okay, this is the max. You see, you have 10 here. Okay. Now you look at here, Q1. Where is Q1? Because Q1 is connected to NAND gate and also Q3. So Q1 is here and also Q3 is here. At this point, this is high. Okay. And then, is it high? Okay. Okay, and also this is here. This is called a glitch. Okay. When both high here, high, high. High and high is high, but not high, it becomes low. So that's why it's clear here. Okay, it will clear at this point. Okay. You look at this NAND gate. This is NAND gate, right? Okay. NAND gate is to clear at that point. At this, what clock here? Clock number 10 here. Okay, because decade you have only 10 bits. Okay, now if you look at here, Q1 is connected to NAND gate and Q3 connected to NAND gate. So Q1 is here. Okay, you see here Q1, it's low, high, low, high, low, and then it start going high here, right? At this point, right? This is high. Okay, now look at Q3. Q3 also high at this point because here is low. It refers to the negative H of Q2. So low here and then it's going to be high actually. All the way is higher here, right? So meaning Q1 is high, Q3 is high. High and high is high, not high, it becomes low. So then you have low here. So it will clear the line there, okay? Or the what is in the counter there. It will clear. Stop there. Okay? So Tan, understand Tan?
Then I try to understand. The glitch I understand already. But how is the 10 digits going to form? Like try draw the diagrams again.
Okay.
The
Okay. So this look at here. The NAND gate is all connected to JK flip-flop here. So this is the clear terminal here. So it will clear whatever inside here. So it will start to count again. It becomes 0, 1, 2, 3 and so on. Okay? So this
Doktor. Maknanya kiranya yang tu 1001 kan? Kiranya yang clock yang ke-10 tu sebab 10 yang maksimum dia 10 kan, 1001. Lepas tu maknanya bila nak masuk 1010 tu dia jadi kosong balik lah kan doktor?
1001 tu masih ada.
Bila nak masuk 1010 ni tak boleh sebab dia kosong balik kan? Sebab dia apa?
Sebab dia dah ada glitch kat situ. Dia clear. Sebab bila ni low, nampak tak ni dekat ni low, dekat NAND gate ni dia di low kan? Bila dia low, dia connected all to this terminal here. See? This is the clear punya terminal. Dia akan clear whatever inside here. So dia tak boleh pergi dah.
Oh, okay, faham.
Okay, but you see here, this is negative. Tengok ada bubble here. So this is all for low active here. Active low input here. So this will clear all inside here. Okay. Faham dah?
Faham doktor. Saya faham.
Okay. Siapa tu yang tanya tadi?
Hafiz, doktor.
Okay. Okay, now look at the 74LS93A, asynchronous counter. Okay, it has one independent toggle JK flip-flop driven by clock A, okay, CLKA ni, and 3 toggle JK flip-flops that form an asynchronous counter driven by CLKB. Okay, so the counter can be extended to form a 4-bit counter by connecting Q0 to the clock B input. Okay, 2 inputs are provided that clear the count. So now this is a 4-bit here. We have 1, 2, 3, 4 JK flip-flop. The first counter, the clock is connected to clock A, external here. Okay. The second stage here, the clock is connected to clock B. And then the subsequent stage here, the clock is connected to the Q from the previous one. So meaning this is third stage, the clock comes from second stage. The final stage, the clock comes from the third stage here. Okay. Okay, then you have here R01 and R02. Okay, wait, R01 and R02 is, okay, gated reset. This is a gated reset input. Okay, this part is gated reset input. So when both high, okay, the counter is reset to 0, 0, 0, 0 state, or it becomes clear. Okay, this is a reset gated. So when these are both high, so when high becomes high, not high because you have bubble, not high becomes low. So when this all low, it clear all the state here. Okay. So all JK inputs are connected internally high. It's mentioned here connected internally high. That's why the wire is not drawn to connect to high, because it's mentioned here is internally already high. Yeah? Okay. So this is Q0, Q1, Q2 and Q3. You can see here this number here 1, 14 here, this all the pin number for 74LS93A here. Okay, that's finished about the asynchronous counter. Now we look at synchronous counter. So look at the spelling here, you don't have A in front. So this is synchronous counter. Okay, so in asynchronous meaning this A is, okay, is far from synchronous, so this refer to 1, not this previous asynchronous. So in a synchronous counter, all flip-flops are clocked together with a common clock pulse. Clocked together with a common clock pulse. So look at this diagram. So you have this first stage, second stage, third stage, the clock all connected to one clock. That is the difference between asynchronous and synchronous. Synchronous, one clock connect to all. Okay? Asynchronous, one clock only connect to the first stage. The following stage, the clock are connected to the previous stage of the flip-flop. Okay, so synchronous counter overcome the disadvantage of accumulated propagation delay but generally they require more circuitry to control states changes. Okay, advantage. Apa dia? What is the advantage? What is the advantage of synchronous?
Overcome the propagation delay.
Sorry, I cannot hear you.
Overcome the propagation delays.
Yes, overcome the propagation delay of the asynchronous counter just now. But the disadvantage, it requires, okay,
Control states.
more circuitry to control state changes. Of course, when you have advantage, there is always disadvantage. Okay, it's like a win-win situation. You want to get this better, you have to accumulate, consider this disadvantage. If you want to improve this, you will have some disadvantage over here. Okay. Okay, so these 3-bit binary counters has the same count sequence as the 3-bit asynchronous counter shown previously. Yeah. So now you have here Q1, Q0 and Q1 connected to AND gate, yeah, and then this connected to JK flip-flop here. So you can draw the timing diagram and look at the counter, yeah. So the next slide shows how to analyze this counter by writing the logic equation for each input. Notice the inputs to each flip-flop. Okay, this is how to design. Now we going to design the flip-flop, counter, sorry. You're going to design a counter using the flip-flop. So now a tubular technique for analysis is illustrated for the counter on the previous slide. Okay, start by setting up the outputs as shown. Okay, then write the logic equation for each input. So this has been done for the counter. So now you have this counter output here. This part is the logic for the inputs. Okay. So put the counter in an arbitrary state, then determine the inputs for this state. Okay, now you have this already, right? Q2, Q1, Q0 is all 0. So now this is the output. Now you determine what is the logic for the input. So Q0, Q1. So what is J2? What is J2? Irdina. What is J2 then? Irdina ada ke? Ke dah tidur? What is J2? Cecilia? Okay. So J2 will be 0 because look at here, Q1 and Q0. This means, you understand this Q0, Q1 meaning Q0 and Q1. So Q0 and Q1, 0, 0 becomes 0, right? Of course, then here also 0. So now J1 is Q0. Q0 is 0. K also 0. So it becomes 0, 0. So J0 is already 1. So you put 1. K also 1. Okay. Where do you get this? How do you get this equation? J2, J. See here from this diagram here. Aduh. Okay, J2 here. Right. Okay, and then J2 here, K2 here, okay, J1 here, K1 here, J0 here, K0 here. Okay, that is for example here. Okay, so J0, K0 is from there. It's from this equation here. Okay, so here this is always high. J0 A K0 is connected to high. That's why J0 K0 is always high here. Okay, now you have this. So use the new input to determine the next state. Q2 and Q1 will latch and Q0 will toggle. So now look at the next stage here is 0, 0, 1. So J2 becomes what? Negative become what? 0, right? 0, 0, and then J1 is equal to Q0 is 1. So becomes 1 and then 1, 1 and 1. Okay, now the third method here. Set up the next group of inputs from the current output. So this is not finished yet. This is only example to show you how to start with the design. And then number 4 here, what to do here? Okay, Q2 will latch again, but both Q1 and Q0 will toggle. Okay, now look at this. Continue complete table. Okay, this is the complete table. Look at the table first. Farah, do you understand? Farah Hanani. Farah ada tak? No Kairina? No Karina ada? Okay, now look at this table. How do you get this? Refer to Q2, Q1 and Q0. Okay, so for example here 0, 1, 1. So Q0 and Q1 here is 1, 1. So become 1. Here also 1. And then Q0 here is 1. So you have 1 here, 1 here, 1 here and 1 here. So you can do this count because this is a counter, remember. So start with 0, 1, 2, 3, 4, 5, 6, 7 and 0, 0. It's go back to the 0. Okay. So now you can draw the, this is another 4-bit synchronous counter. Okay, so you can draw this. You see here, this is the circuit. So you can draw the timing diagram here. So any question? So you look at here 0, 1, 2, 3 at this point, 4, 5, 6, 7, 8, 9 and so on. Hello, are you there? Okay, this is the 4-bit binary counter, has one more AND gate. Then the 3-bit counter just described. Just now 3 bits you only have one AND gate. Now you have 2 AND gate. Okay, so the shaded areas show where the AND gate outputs are high, causing the next flip-flop to toggle. So this is how you do it. That's what I mentioned just now. So you draw the timing diagram and then for example here, it highlights the point where this is high. Okay, because when this is high, it will toggle here. both high. Okay, and then also here, this is Q2, Q1, and Q0 high. So at this point and this point, this is where it is high. So you look at here. Okay, this is point where it is toggle. Okay, when this is high. Okay, this is a 3-bit synchronous binary counter. Now you look at here, the clock, you don't have bubble here. Okay, so meaning you look at the positive edge of the clock. Okay, so this is the timing diagram you can see. So because J and K is all connected to high here at the first stage here, so you will always toggle at the positive edge. So you have lows, high, low, high, low, high, and so on. And then you look at the stage 2. Q1 is referred to what? The output here refer to Q0. Q0. Where is Q0? This is Q0. Okay, the clock is still the same. You look because we'll use only one clock here. Okay, so it start with low, right? And then low until here, and then it becomes high, and then high, high, and so on. Okay, make sure you understand how to draw this timing diagram. Do you have any question?
No, doctor.
Okay, so this is the truth table for the clock just now. Okay, the N is used to assure that flip-flop 2 toggles properly. Okay, because this is not connected to the high, it's connected to Q0. So you must look at the Q0 here for the J1 and K1. And then you have BCD decade counter. So with some additional logic, a binary counter can be converted to a BCD synchronous decade counter. Okay, after reaching the count 1001, then the counter recycles to 0000. Okay, so now look at the diagram here. It has different circuits, slightly different. Okay, you have AND gate here, you have AND gate here, and then you have AND gate and OR gate here. Okay, so this gate detects, as mentioned here, 1001 and causes flip-flop 3, okay, here, to toggle on the next clock pass. Flip-flop 0, which is here, toggles on every clock pass. Thus the count starts over at 0000. Okay. Okay, so this is the BCD decade counter. If you look at here, this is the timing diagram. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes back to 0. Okay, so this same waveform can be obtained with an asynchronous counter in IC form. Okay, using 74LS90. It is available in a dual version. That is 74LS390, which can be cascaded. It is slower than synchronous counter. The maximum count frequency is 35 MHz, but is simpler. And then you have 10 suku Okay, you have 4-bit synchronous binary counter. The 74LS163 is a 4-bit IC synchronous counter with additional features over a basic counter. Okay, it has parallel load. Yeah, parallel load here. Another load here. Okay, and then a clear input here. 2 chip enables. Okay, enables here. And a ripple count output that signals when the count has reached the terminal count. Okay, so it has here, you have here the RSCO here. Okay, and then this is the 4 bits input and this is the data output here. Okay. Example of the waveform, you can see here, this is the counter. You see, because the input just now is in parallel, so you have input here. Okay, and then this is the output in parallel. So you look at here, this is the point when it is clear, because this is clear when it is low. Okay, pay attention to this diagram, yeah, because when this is low, it will clear all inside the IC, and then when it is low, it will load, then it will start to load the data. Okay, alamak, sorry. Okay, it will start to load. For example, here you have 1 1 0 0. 1 1 0 0, it will start to load and the clock is at positive age. Remember, because you look at here, there is no bubble. Is it bubble? Ish. Okay, mana dia? The clock. Here. There is no bubble, right? So, you look at the positive age. So, when it is positive age, you see the clear is low, then it will clear. And then, look at the positive age here. Positive age here, load is low, so it will load all the data inside. Okay, so now it will already load in the IC. Okay, this is point where it is start with the preset. It will load here, so you have high, high, low, low, and then it will start to count. Okay, at positive age here, because 1 1 0 0 is 12, then it become 1 1 0 1. That is 13, 14, 15, and then it start to become 0 again. Okay, so this part is to count. When this, you see enable here, this is high, it start to count. Okay. So it will inhibit when this enable here is low. Okay, any more question? Okay, we finish here. Any more question? Yeah. Uh-huh. Uh-huh. Dia, okay sekejap Saya bagi dia besar. Mana dia? Okay, dia, this is the clear, everything right? Okay, and then it will start to load. But your data is load at 1100. Okay, data is the input that you put inside there. Okay, so you want the data to start with 1100. So 11 here, D3 is the most significant bit here. So this 1100 is 12. Okay, it goes inside there, it start with 12. Okay, so the output you will see is 1100 also. And then at this positive age here, the clock is at positive age, right? Then you refer to this enable here. Okay, enable is for, I think for active high just now, in the IC just now. So when this is high, it start to count. Okay, now it's 12, become 13, 14, 15, still counting. But this is only for 4 bits. 4 bits, the maximum is only to 15 because 1, 1, 1, 1, remember? Okay, and then it go back to 0. So that's what you have here. 0, 0, 0, 0. It count. Okay, sorry, not the RCO here. Here. 0, 0, 0, 0. and then it becomes 0001, right? For this clock. See here, this second clock here, positive age. Okay, but it cannot count after 2 because at this point, this enable here become negative already. Okay, when this is negative here, it inhibit. It inhibit meaning it stop. Okay? So it stop only to 0, 1, 2 only. It's not going to the next clock here. It's supposed to be this clock here, right? At this point. But because the inhibit, the enable here, it's low before the next clock at this age here. Can you see my cursor there? So that's why it stop. It's inhibit there. Okay, question just now?
Then what is ENT means?
That is enable. ENT je. Wait. Yeah. It's mentioned just now. I think enable. Wait. Cannot see. It's very small. Ripple clock output. Reach. Wait. Ripple. Okay. This is ripple. Okay. Look at here. This one first. RCO here. This is ripple clock output. Okay. RCO ripple clock output. Reach high when the counter reach the last state. Okay. Okay, that is it. And then that is the reset. The ENT is enable. It's mentioned here. Wait. See here. It has parallel load, clear input, 2 chip enables. This is enable. 2 chips enable.
Why need 2 enables?
Oh, then you have to check the spec in the 74LS163 here. Okay. I don't memorize everything. Okay. This is only for enable here. And then this is ripple count output here. Okay. Okay. So can we have like 10 minutes rest?
Yes,
before you can have your quiz. Okay, prepare for your quiz. Quiz number 6. From chapter, which chapter? We're going to have from this chapter. Okay. Function of combinational logic. This one we haven't had our quiz yet, right? Don't I think so. You're going to have a quiz. Kenapa tak bergerak benda ni? Mau ada kelas. Kenapa? Mau rehat sekejap. Lagi quiz. Lagi ada quiz. Hello? Semua ada ke ni?
Ada doktor.
Okay, so prepare for your quiz. Take a piece of paper, write your name and matric number
value inside it, it will give you.
apa dia? Okay, dah ready? Okay, number 1. Okay. Dah. Okay. Dia dah? Number 6 dah? Okay, number 7. Okay. Finish? Okay, submit ni Putra Blast.
Pak, question.
Apa dia? Someone to ask
Tadi
me
saya tak
question.
nampak question 7.
Kenapa?
Question
Ya.
6
Hello?
boleh doktor.
Doktor boleh tengok soalan 6 balik tak?
Tadi tak nak bersuara. Sekarang ni orang dah tutup baru nak bersuara. Nombor berapa? Dah tak boleh review dah. Number? Okay. Finish? Don't keep quiet because I don't want to repeat. Okay, number? Next. Finish? Any more ni request? Okay, finish Okay, upload input 13. Okay, since we have about 15 minutes before 11 o'clock, so
Create circuits
you
that can store
check
state.
this video
Circuits that store state are called sequential circuits and are created by feeding the outputs of the circuit back in as inputs. In this lecture, we introduced the SR latch and later the D latch, which both store 1 bit of state. The SR latch is the foundational sequential circuit that we use to build all other sequential circuits. The circuit is composed of 2 cross-coupled NOR gates, where the state that we are storing is called Q, and the complement of the state is stored in Q prime. To demonstrate how the circuit works, let's assume that we do not know the values of the state or its complement, but that we will input 0 and 1 to R and S. If either of the inputs to a NOR gate is 1, the output is 0. So we know that Q prime will be 0 regardless of the feedback from Q. Since R and Q prime are 0, the state will be set to 1. Let's change S to 0. When both S and R are 0, both Q and Q prime will hold their values. Now, let's change R to 1. Because R is 1, the state will reset to 0. Because both the state and S are 0, Q prime will be 1. Finally, let's change S back to 1. Because both R and S are 1, the state and its complement are now both 0. Since we do not want the state and its complement to be equivalent, we say that this input combination is forbidden. We can describe the SR latch's behavior with 2 tables. We use the first table when we know the inputs and the value of the current state Q, and we want to know the circuit's next state, Q+. So here we see that the first input combination holds the current state into the next state. The second input combination resets the next state to 0, hence why R is 1 for reset. Third input combination sets the next state to 1, hence S is 1 for set. And the final input combination is forbidden. We use the second table when we know our current state and our desired next state. The right columns tell us what input combinations will allow us to excite the desired next state given the current state. Now, the SR latch is useful, but we can make its operation simpler by forcing the 2 inputs to be complements of each other. Now, when we make our new data input 0, the input's complement will be 1. This will reset the state of the latch to 0. Q prime will also become 1.
When we change the data input to 1, the input's complement and the Q prime become 0. Then the state of the latch is set to 1. We can describe the D latch's behavior with the same tables as before. Notice that the next state is always the same as the data input. Much simpler, huh? When we design sequential circuits, we want to synchronize the times when all state storage components store new data. We synchronize these components with a signal called the clock that oscillates between 0 and 1. To help synchronize components, we can add a clock command to our latch that acts as a gatekeeper that allows the latch to change its value only when the clock's value is 1. For example, suppose that the data input has the following waveform, and they want to determine the state of the D latch. Initially, we do not know the state of the flip-flop, but whenever the clock is 1, the latch can change the state, and the latch's state will equal the data input. Whenever the clock is 0, the latch will hold its state constant and ignore the data input. This gated latch is not ideal though, because we must hold the data input at the desired input value for half of the clock cycle, and that cuts down the time that we have to perform calculations during the clock cycle in half. An alternative clocking method for synchronizing state storage components is called edge triggering. When we use an edge triggering clocking scheme, we call the latch a flip-flop. When we have a positive edge triggered flip-flop, we draw the circuit components as shown above, and the flip-flop reads and stores the value of the input only when the clock rises from 0 to 1. So again, we do not know the flip-flop's state to start, but at the first positive clock edge, the data input resets the state to 0. Then, at the second positive clock edge, the data input sets the state to 1. The flip-flop ignores the data input at all times except during the clock edge. If the data input ever changes close to the clock edge, the flip-flop will store the value of the input from just before the clock edge. When we have a negative edge-triggered flip-flop, we add a complement circle to the diagram, and the state of the flip-flop will update only when the clock falls from 1 to 0. Let's recap. We created a sequential circuit called a D-latch or D flip-flop. The D-latch or flip-flop stores the value of the data input only when the clocking scheme permits the component to read the data input. Different clocking schemes will store the data differently, so we need to carefully choose our clocking scheme and how we send data to these synchronized sequential circuits. Schemes will store the data differently.
So if you have finished upload your answer in Putra Blast, look at this YouTube, this slide. Okay, this shows the difference between the gated D latch and the positive edge triggered D flip-flop. Yeah. So this is the gated D latch. Okay, you see here is the clock, and then this is the D data. Okay, D. This is data goes in. Okay, and then look at the Q. Okay. For example, here you start with here with no input yet. Okay, we do not cannot determine what is the output here, so that's why you have here like dash here. Okay, and then look at here. This is the clock. Okay, and when the clock is high, this is high, this is low, this is high. You see the data is low, so it follows. And then when data is high, okay, the output also high. But now this clock is low, so there is no change here. So it's going to be high even though this clock is low here, or the input is low here. So here is going to be high until this age here is still high. Okay, and then when this is going, the data going low, it's going low, and then it stays low here. Why? Q follows D. Okay, for gated D latch, Q follows D when clock is high. That's why you have this kind of output waveform. And then here is positive edge trigger flip-flop. Positive edge. So you look at this positive edge here. Okay, for example, this is the D. You see the input waveform is the same for gated here and also for the flip-flop here. But the output you get the different output because it refers to the positive edge here. So let's say you start with low here. Okay, at this clock, nothing happened because this is low. So you low here until this edge here. This edge here is high. So it's going to be high until the next clock. So look at the difference between gated D latch and D flip-flop. So guys, do you have any question? Hello?
Question, doctor. Actually, doctor, can I request doctor to send the YouTube link into the group? Then later I can do it.
Yes. Which one do you want? Which one do you want?
Send.
Which one?
If every day.
No, I want you to be specific. Which one do you want? Because I want to make sure that you are, you know, pay attention to all that I have, go through with you in class or YouTube also, because some of the YouTube are very, it's very good explanation, easy to understand, because it's difficult to explain. I'm here, you there. Okay, I don't have this kind of good slide. Okay. So which one do you want?
Doctor send me the design, the marks one, the first one.
Okay. Any more questions? Where is everybody? Sleeping? Please make sure you understand, because second test is based on what? Start with from adder and then marks, demarks, what else? Decoder, encoder, timing diagram here, and then make sure you know how to draw it, flip-flop. So all those will be covered in test 2. So make sure you understand how to draw the timing diagram. That will surely be asked. Okay. Okay, any more question? Semua tidur je ni. Wis mana lagi? Dah habis kan? Pukul 11 saya dah off dah tu. Dia punya upload tu. Make sure you upload before close dia punya time dia. Okay, so see you on Wednesday.